All right, we're back to this again. So this is going to be RK4, maybe RK3. I'll decide later if we want to do RK3. But first of all, we're going to do import again, and obviously import NumPy, and already here as MP for short. And then we're going to import again. We're going to do MATLAB bim dot, I believe it was called myplot. We're doing that, and then we're going to say as PLT. Uh, So we're starting from here. We're back again. And there's a few things I want to do, and we're going to do something called a definition. And definitions are basically like functions in MATLAB. There's a few things I want to do. There's going to be RK4 we're going to do. Obviously, RK4 is something powerful. And we'll start with RK4 actually. Definition of RK4, right? What is RK4? And then we're going to call it step. And we're going to do parentheses T comma X comma H. And then we're going to do a mark like this. And we're going to tab it out. And we're going to do K1 equal to F parentheses T comma X. And we're going to do a stability analysis like always. But I want to note over here what we're doing first. We're doing K1. And this is why are we putting K1 physically? I mean, we can derive it, yes. But physically, what is a function of getting a K1. K1 gets a value at K1, basically just a value at that point. And now we're going to add some plus H variable to increase what the possible future we can do. Because if you think about it, what is initial condition? Initial condition is we have an ODE and we put that initial condition or PDE and we just push out the answer. We just publicate it. Like we just push, 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 push. And then we see something happening. So what does that mean? With just the ODE and the initial condition, we're figuring out a future. And similarly, what does the numerical methods really mean is that we're using the same kind of idea to iterate. Like we are gonna to iterate, not iterate, sorry, to seek the future. And then that's why we're gonna do K2 equal to what we call a function of t plus h divided. There's a whole entire like proof-based thing here, but for now we're just showing you what is going on. Maybe we'll do the proof later on how they were derived because I think one time maybe you want to see it. But for now, we're just going to show you that this is what people are thinking when we do this. So what we're thinking is basically we are pushing. So this is a plus h divided by 2. So we're pushing the envelope. We're pushing the envelope. We're getting to the future state point from a certain push from the ODE. Okay, so we got that. And you can guess what K3 is. It's a certain push to a direction that allows us to see what will happen next. So RK3 is the same thing, and you're going to use RK, no, we're going to do RK3 is going to be H divided by 2, and it's going to be X plus H divided by 2 with K2, I believe. So this changes. And then what is K4 over here? And that is again, but this was going to be H because this is a full step now. And then we're going to do, I believe, is K3 over here, and then it's going to be H. I think that's right. And what that's going to return to the user, so we're going to return something to the user. And that return will be considered X plus, I believe. And then X is basically the initial. So what we're saying is basically X is starting everything. And then whatever the average of these things, which is going to be average divided by 6, is the push to the next direction, is basically the intuition you need to get. That's basically the whole entire intuition. So I believe it's H divided by 6, if I remember correctly, and you need to parenthesize this for habit's sake. And then you're going to do parentheses over here. If I remember correctly, it is K1 plus I'm just gonna look it up. 2 multiplied by k on the K2 plus 2 multiplied by K3 plus K4. Okay, so yes, and you can see what I'm getting at it. 1, 2, so this is 1 plus 2 plus 2 plus 1, which equals 6, and we see we divide by 6. So this is a complex step push, basically, is what is happening. Basically, it's a complex step push. But why on earth would we want to use something like this? And now we're going to go do a stability analysis here next, which will show you why it's important. But to do a stability analysis, we need to learn the Taylor series RK4 kind of the general Taylor series of it because the fourth order. So you're going to get a Taylor series that is something like, I believe correctly, it's plus check. It's plus xz multiplied by square, and then it's going to be divided by 2, and then it's going to be plus z multiplied by 3, I believe, divided by 6, all right, plus z multiplied by 4, divided by 24. And now this is all have to be less than 1, if I remember correctly, and then we're going to use x real. No, that's going to be outside the function. X real equal, I believe, is going to be line. No, it's going to be NP, right? Because it's from the numerical numpy. It's going to be lean line space. I'm dumb. It's a simple line space, and we'll do -5. No, we'll do -4 comma 4 because I believe it's the stability analysis show up to 500 if I remember. Oh no, it was like what was it called again? It was near it was near, I don't remember, it was near 2.5 where it succeeds. So it's going to be NP dot line line space, and then we'll just line space, and then we'll just do the same thing. Negative 4 comma 4 comma 500. Yes, and then we're going to have to do what we call x comma y. Oh, oh no, 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 no. R comma yi, and then we'll do this. I believe it is called z equal um x plus 1, I believe is multiplied by j, which is imaginary, multiplied by y, and I think you just do 1I, and then that should give you imaginary if I remember correctly. And then this, let me just double check. Yeah, that is how you do it. All right, 1I, and then that is going to be, we're going to get r underscore the absolute equal np dot absolute, and it's going to be just, where was it? Over here. We call, oh, I forgot this, and then we put it here. We do a parentheses here real quick, and then we just do a z like this. And this should be a functionable. Did I make a mistake? I guess I did. What did I make a mistake? Oh, over here, x. This should be a functionable. No, uh, let me see what I did wrong. No, I think that's right. I don't know what I did wrong. It's absolute R. Oh, what the return? The return. We should be good. Okay. There we go. We did the right thing. Okay. All right. That took a while. All right. We're gonna use okay. So next up, we're gonna do what we call a PLT contour. So PLT dot I believe it's contour, and it will be x comma y, and there will be r absolute. Okay, r absolute, and this would be less than or equal to 1, and then it's gonna be just uh, doing that. And you see this? So what this means is anything that is inside of here, as we figure out, is stable. Outside is unstable. So what does that mean is that this is lambda with an h, and lambda with a, I believe it's imaginary and real. So this is lambda with the real and imaginary, and then no, imaginary is over here, real. So if there's something imaginary, it still functions, and that's the whole point of RK4. So we can have a full sinusoidal thing. And a good example is we're gonna do a reverse pendulum maybe. A reverse pendulum will go like this and then back. And then we'll prove that that is true. And then, okay, here we have it here. What we did earlier was just put some labels down and that's it. What we're going to do is we're going to do the reverse pendulum, and then we're going to need a little bit of a definition over here, which is fine, we'll get it. But first of all, this is how clean it looks now. And now we're going to do definitions, which is going to be like the same thing as in MATLAB, where we call upon many things. So we're going to call upon this as g equal 9.8, 9.81. And then we're going to do L equal 1 for simplicity. You can do the different things. And then we're going to call d theta equals omega. What we're doing is making a way for us to get x dot. This is the same thing as state space, where we do like a model and then we do a reduction of order and we do all that stuff. We're doing this little thing in MATLAB a long time ago, I remember. And then we're going to d omega. And this is d omega, which is the acceleration, which we know from physics that this is g divided by L. And it's going to be parentheses. Oh, I should probably explain how we got that, which is basically, why is it? Basically from looking at a system and looking at how it would function. If this is data over here, we see a kind of like what forces will cause going over here and over there, or we can use momentum. I think a lot of people would use force of momentum, I believe, to get this, because with this you can get because I use double dotted omega and theta and those variables, which is considered theta and then theta dot and then theta double dot, which you can get by doing this over here by getting it over which is considered I omega dot or equal to I alpha double dot, no, theta, and which equals I alpha. Sometimes we call this variables. But as you can see over here, what is I? I is a length to multiply L. No, I, oh, there's no G because it's not force. It says ML. L multiplied by L, and then it's G over here, and then, sorry, my mistake. Sign over here. And you can see where this came from. We just do the rest down, and we get the full thing, and this is G over L. My mistake. There we go. But you can kind of see where this ODE is, I'm just going to continue and you will just see it. But it's going to be NP dot sign, and then you can see over here we'll choose theta. And this is why this is called a nonlinear ODE, as well as ODE, but yeah, it's ODE. And then this is where we return an array. We're going to return something here, and we're going to do np dot array, and we're going to do a parentheses by the books. So we're going to do a bracket, and we want two things out of here, and it's going to be d theta first of all, and d omega. What does this really give? Is d theta is the velocity. Oh no, d theta is the omega, which is the angular velocity, and d omega is the angular acceleration. That should give you all the context clues you need to start doing a time step, which is 0.001. Let's just do this, and then t equal, I don't know, 10, and that should be fine. And then you can do t equal np dot weighing by 0, 0 comma t plus h comma h, and then that will get rid of every problem. N equal the length of time because you need that much integers. And then x, now here's going to be a two-part needed initial condition because you're going to do what we call, what we did was basically have a bunch of, we have two ODs that we're integrating, basically, no, I mean, I just discussed this earlier, I think. That's why we had the array problem over here. So these two are basically giving out that basically you have, if this is data dot and this is data double dot, then you get so forth what we see. Yeah. Well, we can't do a matrix because usually if you linearize it, we could do this where we have this kind of combination. But we can't do that. Instead, we have to do it this way, which is less matrixy, but still gives an appropriate answer to what we're trying to do if we're not trying to control it. And this should be a huge sine wave, or not sine wave, but a huge like fluctuating wave because we are not controlling anything. Remember, we're not trying to control here. We're trying to simulate the natural response of how a pendulum would function if this was how we have shown it. And right now, we have shown it as this. And for, here's the interesting thing. So it's a 4 index. So here's the thing. In MATLAB, we could have done, I believe, this to n. But in Python, is 0 to a number. So the integers are 0. So you have to do range n minus 1. Because of that one factor integer over there, you need to do that. And then obviously, what we're doing is we're doing I, right? I. And then over here is telling you how many times to do it. So we are going to +1 to see what will happen in the next step, not the current step. And then we're going to say that equals to RK4 step response. So here. Now, what do we put in this place? We put T bracket I, and we do comma, X. I think that's right. And then it's going to be comma, what did I put for that? Just H, and we already have H, so we're good. And then we just do plot dot plot, and then we do T comma X, and it's gonna be bracket this comma 0, and it should theoretically be right, but I probably made a mistake somewhere. There we go. Oh, okay. Here we just do figure plt dot figure, and there we go. There you have it. A beautiful sine wave. So basically, I can clean it up, but it doesn't really matter. Basically, over here is basically like this. And when you're going like this, you're getting, and then going all the way up here, basically. And then you're flipping it all the way down, so back to the original. So this is what kind of periodically will continue to happen as we grow. And let me just clear this and then just give you a bigger time space. Don't know where, but we're in imaginary space. All right, we're done now, so I'm gonna stop recording.